Lesson 33, Hypothesis Testing Procedure for One Population Mean. If we have an idea what the value of a particular population parameter is, we can test to see if that's a valid idea or not using hypothesis testing procedures. So if our hypothesis involves just one population mean, we could use the following steps to guide us through our hypothesis testing procedure. Hypothesis testing procedures begin with the formation of a hypothesis. A hypothesis is a stated assumption, belief, claim, or idea regarding the issue under investigation. The stated hypothesis must be expressed in a form that can be tested statistically. Because initially, these hypotheses are expressed verbally, but we need to express these verbal ideas in such a way that we can test them statistically. That is, they must be expressed in a mathematical form. The hypothesis testing procedure uses random sample results to determine the validity of the hypothesized value of the population parameter. Thus, a single stated hypothesis generates two competing conclusions to choose from, since the stated hypothesis is either valid or invalid. The two competing conclusions are expressed statistically. One is labeled HO. This is referred to as the null hypothesis. The other is labeled H1. This is referred to as the alternative hypothesis. HO and H1 are opposite conclusions, since only one is valid and the other is invalid. There are 6 forms in which the population parameter can be tested statistically. That is, we could either hypothesize that the population mean mu equals a particular value, or the population mean cannot equal that particular value. The mean could be less than the particular value, or the mean could be greater than the particular value. The mean could even be less than or equal to the particular value, or the mean could be greater than or equal to the particular value. So these are the 6 forms in which the population parameter can be tested statistically. The forms that include the condition of equality are always labeled as HO. So the equals, greater than or equal, and less than or equal are always labeled as HO because they contain the condition of equality. And the HO is paired with their opposite form, which is labeled as H1. The opposite of the equals is not equals. The opposite of greater than or equal is less than. The opposite of less than or equal is greater than. So each of these, the not equal, less than, and greater than, are labeled as H1, and they are paired specifically with their opposite in HO. So the first step in the hypothesis test procedure is to select the paired forms of HO and H1 that correspond to the stated hypothesis. We're either going to conduct a test that involves the HO of mu equals a particular value, mu sub 0, versus the H1 that the mean mu does not equal that particular value, mu sub 0. Or the test could involve HO of mu being greater than or equal to the value of mu 0 versus the H1 that mu is less than that value of mu 0. Or the test can involve an HO of mu less than or equal to the value of mu 0 versus the alternative H1 that mu is greater than the particular value, mu 0. So even though there are 6 different forms, they go together in pairs with their opposite, because either one is valid or it's not valid. And so the resulting HO and H1 has one is valid, one is not valid, resulting in the 3 pairs of the 6 forms of the hypotheses. Next step is to select alpha, the level of significance. Unless there exists a compelling reason to do so otherwise, hypothesis testing procedures are conducted using the customary 5% level of significance, or 0.05 decimal. Next, t-test. After the random sample data has been entered into a list, or the sample statistics, x bar, s sub x, and n, have been determined, the t-test command on the TI-84 calculator will calculate the desired p-value for the hypothesis test procedure. It's this p-value that is used to reach the decision in our hypothesis test. So on the TI-84 calculator, the t-test command is found by pressing stat, arrow over to tests, and arrow down till the cursor is next to t-test. Press enter to select. We can either input the actual sample data into a list. To do this, we press enter under data, and then down arrow where we specify the actual mu0, which is the actual value in the hypothesis. List is where we enter the data. Freq, short for frequency, is 1 because typically each data value comes from one sample subject. And then we match the inequality in H1 with the calculator. It's either the not equal, the less than, or the greater than. We put the blinking cursor on the one that matches our H1 and press enter to select. Then you could go down to calculate. Or we could have, instead of the data, the sample statistics to input. To do that, we arrow the cursor over to stats, press enter to select, and then down arrow, we enter the specific number value, denoted as mu0, that's in the hypothesis. Then we enter in the value for x bar, the sample mean, the value for s sub x, the sample standard deviation, and the value for n, the sample size. Then we match the H1 in the test with the not equal, less than, or greater than in the TI-84 calculator. And then we can down arrow to calculate and press enter. The t-test command displays several results, but in the hypothesis test, we're interested in just the p-value. The p-value is denoted as p equals. So we look at what p equals on the t-test command screen, and we use that to reach our decision in our hypothesis test. Now, the standard score for the sample mean is used as the test statistic for this hypothesis test procedure, and it's the one that is programmed into the TI-84 t-test command. It involves the sample mean x bar, the hypothesized mean value mu sub 0, and the sample standard deviation s sub x divided by square root of the sample size n, which is our estimate for the standard deviation for the sample mean x bar. The corresponding p-value is calculated using the results of the central limit theorem. Therefore, in order for the normal approximation to be reasonable, either the sample size must be sufficiently large, that is, n is greater than 30, or the distribution of the population from which the random sample was selected reasonably follows a normal distribution. So the normal approximation produces reasonable results in the calculation for the p-value when the sample size n is greater than 30. But in cases where the sample size is not sufficiently large, if we can, in addition, assume that the distribution of the population from which the random sample was selected follows a normal distribution, then using the normal distribution to calculate the p-value will still produce reasonable results. Now, the calculated p-value is used to reach a decision regarding the validity of the form of the hypothesis indicated in HO. Small p-values provide sample evidence contradicting HO. Large p-values provide sample evidence consistent with HO. When HO is rejected, the form of the hypothesis expressed in HO is considered invalid. Consequently, the form of the hypothesis expressed in H1, which is the opposite of HO, is considered valid. So we reject HO whenever the calculated p-value is less than or equal to our alpha, level of significance, which is typically 0.05. So when the p-value is less than or equal to 0.05, we will reject the HO, indicating that the HO is not valid. Consequently, means that the opposite idea, H1, is valid. Now, when the p-value is not less than or equal to the alpha, we do not reject HO. And when HO is not rejected, the form of the hypothesis expressed in HO cannot be dismissed. But careful consideration must be given when interpreting this decision. That's because either HO cannot be rejected because HO is valid, therefore we do not reject valid ideas, or because there is not enough sample evidence to clearly indicate that HO is indeed invalid. It turns out that sometimes when we do not reject HO, it's because HO isn't necessarily valid, it might be invalid. We just don't have enough sufficient sample evidence to prove this beyond a reasonable doubt. Now, based on the interpretation of the decision reached in the hypothesis testing procedure, that is, whether we reject the HO or do not reject the HO, an appropriate conclusion can be stated in terms of the issue under investigation. Thus, based on whether the conclusion is to reject HO or not reject HO, we then need to state our conclusion in words of the problem appropriate with that interpretation. The following examples will help demonstrate the hypothesis testing procedure for one population mean.